Thanks to the chair for introducing me. I also would like to thank the organizers for giving me this opportunity to speak at this conference QMAT 2026. So today the title of my talk is basically Shubnikov-de-Haas oscillation study of the large magnetoresistance in molybdenum substituted WT2, that is tungsten ditelluride, single crystals. So I am at Central University of Punjab, Bhatinda. So this presentation which I am going to give today is basically based on this work which came out in 2024. This work was actually done completely in the University of Warwick long time back, but the experiments were completed long time back, but the analysis was, we did take and retakes of the analysis, and finally it got published after some time. So I would like to first of all thank my collaborators at the University of Warwick, Professor Geeta Balakrishnan, Dr. Martin Lees and Dr. Paul Goddard. Paul played a major role in this work. Okay, so to begin with, tungsten ditelluride, that is WT2. I think there is some little bit of formatting problem here, but anyway. So what is written at the top is that it is extremely large magnetoresistance, which is called as XMR. And this was first of all reported by Kawa's group in 2014 in this paper in Nature. And the authors coined this term XMR. And in this, they reported extremely large magnetoresistance, which you can see that it is nearly 400,000 percentage at 4.3 Kelvin and 14.7 Tesla magnetic field, which becomes 13 million percentage at 0.53 Kelvin and 60 Tesla field. So that's why they coined this term extremely large magnetoresistance. But this kind of very large non-saturating magnetoresistance is not very uncommon in semi-metals, which have a good electron and hole compensation, means where the electron concentration and the hole concentration are nearly equal. So good examples are like bismuth and graphite, where also we see large non-saturating magnetoresistance. However, at large fields, this magnetoresistance does saturate in bismuth and graphite. However, it seemed like this is the first example of a semi-metal. So WT2 is a semi-metal. So it looked like that this is the first example of a semi-metal where there seems to be a perfect compensation, and there is no saturation till the fields that were obtained in the laboratory. So they call this condition as resonance, meaning that the electron and hole concentrations were nearly equal to each other, and in that condition there was a large non-saturating magnetoresistance. WT2 has other claims to fame, like it is an itinerant superconductor. It goes from the, so you can see that it goes from this large magnetoresistance phase as the pressure increases. So the large magnetoresistance is suppressed, and finally it goes into a superconducting phase under pressure like of the order of 11 gigapascal and further. And this is the phase diagram that was reported in this paper. Further, this WT2 is also a type 2 Weil semi-metal, and many RPS studies and DFT studies have given evidence regarding the type 2 Weil nature of WT2. So at the core of this understanding the magnetoresistance, why it does not saturate at this fields which are obtainable in the laboratory, there is a very basic classical explanation for that, and that is a two-band model. So basically in the two-band model, what is assumed is that there are one electron band and one hole band, both have their own carrier concentrations and they have their own mobility. And in that model, the magnetoresistance very simply comes out, by this expression. And there is a similar expression for the Hall resistivity, which I have not given here. Now, the interesting thing is that if there is a perfect compensation, that is Nh is equal to Ne, and if we further assume for the time being that both the mobilities are the same, then you can see that this B square term in the denominator, that disappears, and this expression simplifies to this condition. That is, the magnetoresistance goes as B square and the slope is proportional to the product of the mobilities of the holes and the electrons. So that is why this two-band model could explain this very large non-saturating magnetoresistance, and the reason was given that the very good compensation of electron and hole concentration in WTE2. Now, there are certain fine details, like if there is even a slight deviation from equality in the hole and electron concentration, then what happens is that the MR will saturate at certain field, which depends on various properties. So both, as I have already told, bismuth and graphite, although they have non-saturating MR at low fields, they do saturate at high fields, and that is why WTE2 was thought to be a fully compensated semi-metal. One clarification I should give is that the two-band model is kind of an oversimplification, because we will see that there are actually more than one electron and one hole pocket. So there are more than just an electron and hole band in this material. So just to give a brief overview of the work that has preceded in this field. So this material shows very good Shumnikov-de-Haas oscillations in its magnetoresistance and also in its Nernst effect. And so a lot of work was done on the Shumnikov-de-Haas oscillations in this material. And you can see here that, for example, here they do the fast Fourier transform of the oscillations to obtain these peaks. So you can see there are 4 peaks here, F1, F2, F3, F4. And these 4 peaks, these 4 peaks in this magnetic field, they are actually the frequencies of oscillations. And each frequency of oscillation actually corresponds to a Fermi surface. Now, the Fermi surface corresponding to these 4 frequencies, they have to be identified as whether they are electrons or they are whole Fermi surfaces, right? So this, in this work by the group of Zhu, they also did some DFT calculations, and from the DFT calculations, this is the Fermi surface pockets that they obtained. So the inner one, like the 1 and the 4, the blue ones are from the holes, and the outer ones, they are actually 2 concentric ones, both 2 and 3 here are from the electrons. And you have similarly on the other side of the gamma point, you have the 2 more hole pockets and 2 more electron pockets. So this was a picture from the DFT, and that is seen projected onto the kx ky plane, kx kz plane. But from the experiments, so they did this analysis of the oscillations with the magnetic field pointing in the the A, B and C directions, and from there they obtained that this Fermi surfaces were actually ellipsoids. So this they are ellipsoids, meaning like the cross sections, so they are ellipsoids with a little bit of asymmetry, like the lengths along the A, B and C directions are not all equal. So similarly, there were other reports where also they reported this 4 peaks, and there were the 2 inner peaks I didn't mention here. The 2 inner peaks like beta 1 and beta 2 are attributed to the electrons, electron pockets, and the outer ones alpha 1 and alpha 2 are attributed to the hole pockets. Here I would like to show here, for example, they did these measurements on the bulk. This is a large magnetoresistance, and this is the Shumnikov-de-Haas oscillations in the magnetoresistance, from where they get this again the 4 peaks in the FFT corresponding to the 4 pockets. This is the Hall resistivity, and from the nonlinear nature of the Hall resistivity, we can see that there is a 2 carrier which are contributing to this Hall effect. They thin down their samples to much smaller thicknesses like 33 nanometers, 6 layers, 7 layers, 12 layers, and that is the Hall effect corresponding to that. So I didn't show the magnetoresistance part. So in the magnetoresistance, still they obtain a parabolic or B square nature. But if you look at this equality of the electron and the hole concentrations, the N by P ratio, that is not 1 actually. So what the people found that mobility rather than the electron hole compensation was more critical for getting a parabolic nature in the magnetoresistance. So many people also used some flakes, and they did some electrostatic gating to deliberately dope these materials either with electrons or with holes. And for example, in this with the gate voltage, they could suppress this large magnetoresistance, and the magnetoresistance disappears as the gate voltage increases, and the Hall signal, which shows initially a 2-band kind of thing with this nonlinear trend, becomes straight, means which shows that it is now only either p type or n type. So once the so if it becomes p type, that means there is no more electron hole compensation, and hence they thought that this 2-band model actually captures this explanation of the large magnetoresistance. This work also more or less does the same thing. They say, show that at a -6 gate voltage, there is a maximum in the magnetoresistance, which is also reflected here in the red curve here. And that coincides with, if you see here the NH and in any plot, they cross each other at around -6, where that means that there is a equality in the electron and hole concentrations, and that corresponds to the largest magnetoresistance observed here. So again, they thought that this is the 2-band model, and that perfectly captures the physics here. So I will just talk about this one here. So what these people found that when they go down to from 24 nanometers to 2 nanometers of thickness of the flakes, they observe this magnetoresistance as B square. And the reason, and although there is not a electron hole compensation, because the electron hole compensation is quite off, it is 1.6 here, still they can see a B square behavior. And the reason they said was that they did a small simulation here. They showed that if the mobility is quite less than the second term, which I have shown you earlier, this term, if the mobility is less, then this term can still be insignificant if even there is a small mismatch. So that is again how they had explained in this work. However, there were certain contradictions, like in this paper, for example, they said that even when there is a breakdown of electron hole compensation, still they get a parabolic magnetoresistance. So they thought that no, that this this 2-band model is not exactly sufficient. There was one pressure study in which we can see that the 4 peaks corresponding to electron and hole pockets, out of that 2 disappear and the inner ones remain. And you can see that the magnetoresistance still remains as a parabolic nature. And since it is critical to have an electron hole compensation, these 2 remaining pockets have to be 1 electron and 1 hole. So that puts it in contradiction, because earlier, as I told you, the inner pockets were mostly have been attributed to electrons and the outer pockets have been attributed to holes. So this was kind of against the trend, because they were now saying that one of the inner has to be an electron and the other one has to be a hole. People have done effect of deliberately, they have substituted a tungsten to find how the magnetoresistance behaves because of this introduction of dopants. So you can see here that with molybdenum doping, for example, here the magnetoresistance, so this is just the resistivity versus temperature. they show that with doping the RR value goes down, which is understandable, and the residual resistivity also goes up. And in this the interesting part is here that they show that mobility does go down, and K is actually the inequality in the electron and hole concentrations that goes up. And so they basically attribute that the electrons and hole asymmetry as well as the going down of mobility are critical to explaining the decrease in the magnetoresistance, which is evident here. A similar work on nanoflakes of MO doped WT2, these people also reported that they reported basically that the mobility was critical and not the electron and hole compensation from their studies. So now I will just move on. So I basically glue these crystals of WT2 using a chemical vapor transport method to basically very quickly to say that it is basically we put our starting material at a low temperature, at a higher temperature, and there is a temperature gradient, and the crystals should grow at the cooler end over a time of 1 to 3 weeks. These are the starting tubes, and then luckily some has crystals at the end of the growth. So these were the WT2 crystals which we grew, and we doped them with molybdenum starting with 0.5, with 5%, 10% and 20%. So we did 5, 10 and 20, which is evident here, and we looked at the 008 Bragg peak, and that shifted to higher 2 theta, indicating that there was a contraction in the C axis. So the molybdenum size is slightly smaller than tungsten, which would explain this contraction in the C lattice parameter. This is the Lau image of one of the crystals, which shows the good quality of our crystals. First we look at the resistivity versus temperature curve, from where we can see that the residual resistivity ratio goes down as we go from tungsten to 20% molybdenum doped WT2. So the residual resistivity ratio goes down, which is important because that it means basically that the transport time, scattering time goes down, and the mobility also, the transport mobility goes down. The magnetoresistance with the doping also goes down, starting from, like in the pure WT2 we have a 9000 percentage, and it goes down to 700 when we have a dope with 20% molybdenum. So here if you look closely, you can see that there are oscillations which survive up to 5 Kelvin or so. So we subtract a second order polynomial from this resistivity versus magnetic field data, and then we obtain these oscillations. So these are the Shumnikov-de Haas oscillations, and we do a fast Fourier transform of these oscillations, from where we obtain this graph here, and they each corresponds to the different compositions, and we can see that clearly that there are 4 peaks as reported in the literature. And we also follow the normal trend in literature. We attribute the first and the last peaks to the holes and the inner peaks to the electrons. We can note that at the 20% one, we do not get the peak for the hole. The last peak is not visible. So these are the frequencies plotted, what we have shown here, that is plotted as a substitution, and we don't see much changes in the frequencies. So basically with doping, the electron hole concentration doesn't change much. So if it was compensated, so initially to begin with the holes were a little bit less than the electrons, but with doping in fact the holes slightly increase, and hence the compensation actually becomes better with doping. We assume that because the anisotropy of the Fermi surfaces, although they are ellipsoids, was not large, as corresponding to graphite, for example, where it can be as high as 12. So we went with a spherical Fermi surface approximation, which is also done in the community, and from that we can obtain the Fermi wave vector and the electron and hole concentrations. So this is the values that we obtained from those frequencies corresponding to pure WT2, 5%, 10 and 20% doped. Yeah, so 5 minutes, okay. So I will just wind up. So basically we see that the electron hole compensation actually improves with molybdenum, which was quite not what we expected. And we did Lifshitz-Korsavich fit to the amplitude of the oscillations with magnetic field, with temperature, and from that we could obtain our effective masses of these four pockets, and they also don't show any significant changes as we do with doping. We did a Dingle analysis with for only the first peak, because we could not do it for the remainder. So the first alpha 1 whole pocket, we did the Dingle analysis for that, which gives us the quantum scattering time. The quantum scattering time is different from the time we get from the electron or the hole mobility, which is the transport scattering time, because in transport scattering time the large angle scattering matters, whereas in quantum scattering time both small and large angle scattering both matter. Again, if you look at the results which you obtain for the quantum scattering, they don't change much with doping, but we infer that from the RRR values which go down, that the mobility must go down, and hence the transport scattering time has gone down, although the quantum scattering time doesn't change that much. Such variation in transport and quantum scattering times have been seen in other two-dimensional electron gases and graphene. So basically, to conclude, what we found was that the two-band model, although is very widely used in this field, can suffer from over parameterization, as it has some mutual dependencies like the mobility of the hole and electron. They can be interchanged, and these electron and hole concentrations. And it also discards much information about the Fermi surface, like there are 2 hole pockets and 2 electron pockets, but we have only 1 electron band and 1 hole band with the same mobility. So what we found, that we could very basically explain the magnetoresistance on the basis of decreasing mobility from the RR values, and even though there is a persistent charge compensation as we observed from the Shubnikov-de-Haas oscillations. So I think that brings me to the end of the conclusions, the presentation. Thank you for your attention.
Thank you, Saurabh, for this nice opening talk. So now we can have some questions.
So why did you choose molybdenum for this?
Well, that is interesting, because actually MOT2 I was also growing, and I grew some 2H crystals. In fact, I have shown the pictures of those at the very beginning. So you can see this is a 2H MOT2, very large crystal which we grew. This is the alpha phase of the stable phase, and this is the beta phase which we quench at 900 degrees Celsius. So I was growing molybdenum, and they were already, I thought that molybdenum would be a nice thing to dope and see how the tungsten telluride magnetoresistance and the charge compensation theory varies with that. So that was the motivation.
So how stable it is?
Which one?
This MOT2.
These are very stable. So once you grow the crystals, they remain like that.
Have you tried to take monolayer with this?
You can do exfoliation, because they're all 2D materials. So you can do Scotch tape exfoliation.
After exfoliation, is it stable? Because generally.
So I have not done exfoliation on this, but I used to do in my PhD on Bi2T3. I did exfoliate and made devices using EBL. But when I used to measure them, they used to get burnt out, either because of static discharge or I don't know, some heavy currents. Because in nanoamperes also, it is sufficient to burn your nano devices.
Yes, sir. Thank you for the talk. Sir, maybe I didn't understand properly. Is the perfect electron and hole compensation is enough for explaining the large magnetoresistance? Or is there any role of the carrier mobility? Because the electron and hole.
So yes, so if you go back to that expression, you can see here that both mobility and hole concentrations have a role. So when NH is equal to NE, this term becomes 0, right? So then if you solve this, it just goes like B square. So exact compensation is required for this non-saturating B square behavior. But as I showed in some graphs for some other works, they have shown that even though there is some mismatch in the concentration, because of this low mobility, this factor, this term is not that important. So it is counterintuitive. Although large mobility is needed for a very large magnetoresistance, but in case if you don't want saturation, even when there is some mismatch, then probably a low mobility is good, because graphite and bismuth, they do saturate in certain very small mismatch because they have very large mobilities.
You have the XRD data of WTE.
Yes, I have.
Do you see any evidence of oxidation of the WTE? Because once you made a crystal, it's exposed to air, right?
Yeah. So we don't follow any glove box anything. We expose it. No, I didn't find any issues with oxygen, neither in the XRD. I mean, the XRDs gave only the 002 family planes because we did on the single crystals, and yeah, I didn't find any issues with oxidation of WT2. The XRD peak is here if you want to see.
So this is only very.
For just the 008, but yeah, I mean only this family of planes was there in the. Okay. Yeah, I didn't do. These are all bulk crystals, so I didn't do on exfoliated crystals. That maybe at that few layers or monolayers there it might be important, but on the bulk we didn't find any issues.
Yeah, are there any further questions? We still have some time. So maybe I can ask you one question. So is there any other property of WTVT that is predicted, like in terms of spin transport or things like that?
Yeah, I mean there are quite a few papers on like they have quantum spin Hall effect and many others already reported in WT2. So because of this type 2 wild nature, many people have done this spin measurements and all these topological measurements, and they have some experimental.
Those are on 2D, like exfoliated.
Some maybe on exfoliated, some on bulk. Yeah, both.
Okay, so if there are no further questions, we thank the speaker again.
Thank you for your attention.